Okay, my name is Dongjae Lee, and I'll start the lecture on the second part of Chapter 3 on representing designs and design knowledge. So we first finished the introduction and talked about the different knowledge-based models of design. And for Chapter 3, Professor Han and Sunjo talked about representing designs, and now I will discuss about the next part, which is representing design knowledge itself and translating between representations of knowledge. So translation means of knowledge representation. So the book describes 4 different types of translational means. The first is existing designs. The second is types and prototypes. Third is design rules, and the fourth is procedures. Existing design is literally it's exactly what it means. It's similar designs or designs that was done previously. The reason why this is a good means of representing design knowledge is because it dealt with the same design problem. So it had the same problem, same constraints. So therefore, using existing designs is a very good means of representing knowledge. And using this, a new design can be used to interpolate new designs and extrapolate new designs. And also, they serve, as I said before, they serve as a source of general rules or principles, and also constrain the production of new designs. And from this, we can also extract new knowledge and from existing designs to produce and improve and find different solutions to different problems. So one example would be the history of mobile phones. So first, we see that the mobile phone had a small display with the number pad, obviously because you need to call someone. And over the years, the form of the shape remained the same with the antenna. However, with new technologies, the antenna didn't need to be outside of the phone. It could be embedded, and it became smaller. And now with the development of smartphones, we have complete screens with several buttons. And now we have very similar looking phones with bezel-less phones filling up the entire phone and without any buttons. And the next is the different types. So design types are systems of abstractions that serve to define classes or design descriptions. So for example, the reason why this is a good means of representing design is because it specifies a different design requirement. So for example, for cars, there are different types of sizes. So for Hyundai, there's the Avante, Sonata, and Grandeur. And the similar sizes for the Kia is the K3, K5, and for the Audi is A3, A4, and A6. So depending on what the customer requirements are, even with the same similar type of design, it can be separated into different types and categories. The next one was about the design rules. So design rules is basically the codes and regulations, so the law of the design. So for example, for a long span, we use a suspension structure, and when we're lifting heavy objects, we use a hydraulic system. So it's a basic law that is decided by experts, which we can follow when designing certain new products and new systems. And we use rules to externalize knowledge. So a rule of thumb is basically what experts use. So it can't be really sometimes it cannot be really described by science or experiments, but by experience, and experts have a rule of thumb. And also there can be a rule of acquisition and textual regulations. Also for the procedure, design process itself is it's a time sequence, so there are rules for design procedures. Because there are so many designs in the past in engineering and in product design, there are certain rules and procedures that must be done. There are a certain number of orders that must be done before another procedure. So do not do Y until X has been completed. So for example, before all the functions have been met, and then do the aesthetic design, or else if you do the aesthetic first, then we'd have to change the internal design again, and it's basically a waste of time. And reasoning takes place by matching the different patterns of new situations and those of the past experiences. So the book describes an example of a design procedure, but this is a very one example. And if you go to Google, I actually searched the design. This is an image of design processes. So there are so many different design processes. Therefore, you can choose and follow several different types. And other than design processes, with design methodologies, there are different design methodologies. So for example, there's the top-down, bottom-up processes. This is a bit of an engineering approach by using QFD. There's also TRIZ, which researches different types of patterns and tries to alter and slightly alter to find new solutions. This one is an example of the axiomatic design developed by Professor Saw from MIT. And so therefore, there are different methods, there's different procedures, and these are different ways of representing the design knowledge procedures. The next topic I will discuss about is the different categories of design. So these are the different categories that the book discusses. So there's axiomatic and heuristic, domain-specific and domain-dependent, conventional versus idiosyncratic, deterministic, non-deterministic, certain and uncertain, precise and imprecise. And I will discuss a bit more detail about each different categories. So this is a design three-dimensional space that the book discusses. So there's the axiomatic, heuristic, domain-specific, domain-independent, conventional, and idiosyncratic. And axiomatic and heuristic so axiomatic knowledge consists of definitions, axioms, and laws. It's basically a result of scientific investigation. So they have been proven, they have been studied, they have been researched, so they're solid laws. So for example, beam theory is pretty solid. It's been researched for over 50, 60 years, and it's basically a law. Heuristic knowledge, on the other hand, is, as I discussed before, is like a rule of thumb. So experts, they're not really justified by scientific or research. They're never a priori, but they cannot be proven. But it's a rule of thumb that the experts follow, and therefore is, in general, a good source. So these are the two axes. And also, heuristic knowledge is therefore, it's a bit shallow because you can't explain it. But on the other hand, axiomatic design knowledge is deep because it's deduced from certain laws of science and fundamental principles. And so axiomatic design and domain-specific and domain-independent is another category. It's a relative axis, and so to say, depending on the boundary of the domain, so what you're designing. Domain-specific knowledge, literally, it's specific to only the domain. And domain-independent is, regardless of what you're designing, it's a general rule, a general design, a general physical law that applies to all the design problems. So for example, the domain-specific knowledge, for example, is the designing of a hydraulic pump and the design itself. However, the independent part would be the knowledge about the design in general and the reasoning in general. And this focuses on the externalizing of the knowledge in a domain without being concerned with how the knowledge will be. So this is another factor that it can be categorized. The next one is conventional and idiosyncratic. It's also a relative term because design itself it can't be categorized into specific with clear distinctions. Conventional knowledge literally means it's generally accepted by a group of people, a lot of experts, whereas idiosyncratic knowledge is accepted by only some individuals, but not necessarily by everyone. So for example, conventional knowledge could be solar panels can be a good source of alternative energy. That's a conventional knowledge that a lot of engineers and designers know and follow. However, the idiosyncratic knowledge would be because there are different ways of producing solar panels. So for example, there are silicon solar panels, there are perovskite solar panels, CIGS. So, and each experts would have a different idea and opinion about that. So one might say silicon is still a good solution. One might say it's too expensive and therefore need an alternative. So this would be an idiosyncratic knowledge that would follow. And so the conventional knowledge would be the connection of design experts, the convention of design experts. And for the idiosyncratic, it would be more of the stylistic approach. So independent, something unique about the designer or the engineer, etc. And the conventional knowledge would be the designer's knowledge base in general, so the basic laws that they follow. And the idiosyncratic knowledge would be knowledge brought by a particular problem, so they need to alter and adapt to the different problems that they would. So this is the difference between conventional and idiosyncratic. And deterministic and non-deterministic is the description is to describe the decision-making process of design. So there's no way of predicting outcomes, and this is what non-deterministic means. Therefore, there needs to be a diagnosis of the solution, problem, to find a solution, and there needs to be a process of generating every possible outcome. And it's also something to do. There is something to do with probability, and it describes. We talked about in previous lectures that design is a ill-structured process. So there is no one certain solution, and there is a lot of different solutions. And for example, this is an example. So there is water in this. There is a water stain on the wall, and by non-deterministic view, it could have been produced by a rising damp, or it could have been produced by a leaking roof. So there is not one solution, one cause of this problem, and therefore it's non-deterministic. And certain and uncertain is a bit further into this problem of the deterministic and non-deterministic, and talks about the probability. It also, therefore, there needs to be also diagnostic. And the difference between the deterministic and non-deterministic is the additional information of the statistical information. And there are techniques for reasoning with this kind of knowledge and propagating values through networks of interferences. So before, this was the graph for the non-deterministic value. And if we look at the certain and uncertain, there is an added value of the probability. So from 80%, it could have been produced by the rising damp. And from for a probability of 40%, there could have been produced by a cause of a leaking roof. And so this is a probabilistic rule about the water stains. And precise and imprecise is also basic literal translation. This talk doesn't talk about the true or the falsity of the statement, but the degree of the statement. So, for example, if the loss of a property is highly critical, then the design must be very safe. It's not something that can be very clearly defined, but by the degree, and so therefore the key point of this precise and imprecise factor is the linguistic variable. So we talk about highly critical, very safe, or very not safe, etc. And therefore the linguistic variable plays a very large, important role. And the quantified linguistic variable can be studied with the fuzzy set theory, which will be discussed in chapter 6, I think. And this was the different categories that was mentioned by the author. And the next part of the chapter discusses about translating between representations, and talks about why and how we need to translate our knowledge from one to another. Knowledge interchange format is a computer program that was designed to do this, and we'll discuss about how the interpretive rules can be translated into frame-based representation. So first is a model. So a model was designed to serve as a framework. So there are different types of designs. There are a lot of different designs. And a model serves as a basic frame, a basic structure for this design. And therefore, this provides a common ground among experts. So for example, medical experts share common models of the human body, for example, the skeleton, and common models of the diagnostic practice. So if everything was different, then the doctors would not be able to discuss something. But because the human bodies have a specific form, they created a model, and therefore the experts can discuss. So for example, if they talk about the third bone of the rib cage, then they know what they're talking about. And because of this model, it provides a basis of communication. So for example, a auto mechanic can study the model and still fix different types of cars. So for example, a car has a basic engine, etc. So even if they open a different car, they can still know what it is. So that's a very important aspect. So a very important aspect of design is to follow a model so that it can be used for different types of experts. and a group of people. And another example is, so a model shouldn't have a lot of information. It should be slightly abstract, has less information than a prototype, and also a partial description of a design. So, for example, a model of a house would be, it has a door, it has rooms, windows, a roof, etc. But if we, for example, have a house as something with two windows, then it becomes too restrictive and cannot serve as a model and cannot serve as a communication basis for different experts. So using this model, different experts can discuss and communicate with different methods, CAD systems, expert systems, application programs, databases, etc., and so on. And design models represented as frames is going further on and developing a model, and it's basically a generic model with a frame-based description. So I think it'll be easier to explain with this. So a generic frame is something that has what they call a may have slots. So for example, this is, it's not very clearly, can you read this? I think it's a bit better. So this is building a custom desktop, for example. We have the different components, the different models that the computer requires, so the CPU, the RAM, the graphic card, storage, etc. However, by creating a frame, the users can design a specific, so for example, they can design a higher powered, with a computer with a higher powered CPU, RAM, or graphic card. So these generic frame may have slots, which is basically the function of the frame-based model. And extracting implicit models from rules is basically how, so we have these different design rules, and how can we extract the different models from these rules? So for example, the rule has a statement that if X is a house, then X is a building and has at least one door and is used for living. And how can we extract the data, extract and create models from this rule? Is pretty simple. It's one method is to use generic what's it called? Generic rule. So this is generic representation. So changing this rule into this generic rule is that the superclass, it's a building, and within the class of building, it's called a house. And the properties of a house is that it has at least one door and used for living. And to be a bit more specific and to describe it as frames, so the class name is a house. It's a kind of a building, and it has a number of doors and at least one, and the function of it is living. So by separating each of these rule statements, we separate them and then extract them into different frames. So this is the method that is suggested by the author. And the limitation is that we can only partly construct a model from these rules, and because there's no specific definition, these processes need to be done manually, which is the limitation and disadvantage of the extracting implicit models from rules. So as a summary, from the chapter 3.4, I talked about the representation of design knowledge. So from the traditional representation, there were the existing design types and procedures, and I talked about the various categories that can be used to categorize design knowledge. So axiomatic, very systematic, or heuristic, which is based on experience, domain-specific and independent, which is general, etc. And for the chapter 3.5, I discussed about translating between representations. So I talked about the importance of having models, which provides a common ground for experts, and how the models can be represented as frames. And for the extracting implicit models, I talked about how we have to separate the different rule statements and extracting the knowledge. And however, the limitations would be the partial constructions and the manual process that we would have to follow. That was the end of my presentation. Thank you. Any questions?